Okay, before we start, I would like to ask my colleague Philando to give some information to the participant.
A very good evening to everyone. I think you can hear me. So this webinar will be slightly different because the attendees will be on separate platform. I mean Zoom only, but just differently. So the attendees will not be able to directly ask questions. So you can only use the chat. So we have the Q&A box, and also on the chat, you can chat there, or you can ask in the Q&A section later. And before the end of the program, we will also post the feedback link, and then you can fill up the feedback form. Thank you.
Okay, we'll start the lecture this evening, and it is a great pleasure for the Department of Chemistry to be able to organize this annual SNPAL Memorial Lecture on the topic Understanding the Basic Concept of Nanomaterials. And on behalf of the organizer, I would like to apologize for the last moment postponement of the schedule. However, we are glad because around 180 participants registered in this lecture from various colleges of the state and also from NISER Bhubaneswar. And we are happy with the response of all the participants. And however, at the same time, we are also thankful to the resource person, Dr. T.K. Mishra, for his willingness to share his valuable time with us, although we know he's very busy. So, however, we are very grateful to have him this evening. So, without further ado, let me invite Ms. Marilee Saukume to give a welcome address.
Good evening, everyone. I extend a warm welcome to all the participants to the annual SNPAL Memorial Lecture. I also find great pleasure of welcoming the speaker for the program, Dr. Tarun Kumar Misra, who is the Associate Professor of NIT Agartala. Welcome, sir. So the topic of discussion for the evening for this program is understanding the basic concept of nanomaterials. And this topic was chosen keeping in mind the interest of the students. So I'm very certain that under the able guidance and proficiency of Dr. Tarun Kumar Misra, you will all have a clear and better understanding of the subject. And you'll also have a better understanding about nanomaterials. And I hope you enjoy the rest of the program. Thank you.
Thank you, Mary, for that sweet welcome address. And next, I would like to invite our former head of the department, Dr. Manas Das Gupta, to say a few words about SNPAL. I hope sir is joining yet. What joined? I think sir, Dr. Manas Das Gupta is not yet there. So I would like to invite our head of the department to say a few words for this occasion.
A very good afternoon to all the participants and especially to our resource person, Dr. Tarun Kumar Misra. So first of all, just a little bit about this program. So this program was initiated by our immediate former head of the department, Dr. Manas Das Gupta. So we plan to give him the honor to introduce a little bit about Professor SNPAL because Sir Manas Das Gupta was a direct student of Professor SNPAL. But I think due to network problem, Sir is not able to join here with us. So Professor S.N. Pal is one of the foundation member of the Department of Chemistry, St. Anthony's College. And he was a well-renowned professor who teach chemistry, we can see like the back of his hand. All his students used to enjoy his lecture. And it's a very well-known fact that even students who are not taking chemistry also, even students from the art section and even the commerce section, they will want to attend chemistry class if the class is taken by Professor S.N. Pal. So we can understand, Sir Professor S.N. Pal is a very popular teacher. He is a very good teacher. He was one of the foundation member. And in order to honor him, even in the college also, we have an award which was initiated by the governing body of the college. We have an award which was named after Professor S.N. Pal. And a student of chemistry honors who topped the list in the NEHU result, we can see, used to get this award, which is called a Professor S.N. Pal award. And even our compeer here, the MC of today's event, is one of the topper in her BSc time. So she was also one of the recipients of Professor S.N. Pal award. So that is a little bit about Professor S.N. Pal. And in order to honor him, the Department of Chemistry, St. Anthony's College, we used to host this program every year if we get the chance in order to remember Professor S.N. Pal. So with these few words about Professor S.N. Pal, thank you everyone and welcome to the lecture.
Thank you, Dr. Isideldin Snaitang, for that introduction about S.N. Pal. And in case Dr. Manas Dasgupta join us later, I will invite him again later. And so now, before we go to the lecture, I would like to give a brief introduction about the speaker for this evening. And personally, from my side, I would be very thankful to Sir, though I've already met him for in this year only during the pandemic online, but he's very he is very willingly ready to help us. And during his 2 weeks, we are contacting him. Although he's very busy, he is very ready to help us to give this lecture. Although he is in a very tight schedule. So, Dr. Tarun Kumar Mitra, he is an associate professor in the Department of Chemistry and IT Agartala, and he obtained his PhD from Burdwan University in 1999 and completed his postdoctoral fellowship from the National Taiwan University in the year 2001 to 2008. He joined as a senior lecturer in the Department of Chemistry, DIATF, West Bengal, in the year 2009 to 2010, and later he joined as an assistant professor in the Department of Chemistry, SKFGI, West Bengal, in the year 2010 to 12. In the year 2012, he joined as an associate professor in the Department of Chemistry, NIT Agartala, in which he served as the head of the department from the year 2016 till 2019. He was the chairman of the DPC Chemistry and IT Agartala, and currently he is the coordinator of the Central Research Facility. It is of great honor to introduce Dr. T.K. Mishra, as he is a life member of the Indian Association for the Cultivation of Science, Kolkata, life member of Indian Science Congress, fellow of Indian Chemical Society, and member of the American Chemical Society. His research interest is on functional nanomaterials chemistry, coordination chemistry of cations and anions, and chemistry of small and macromolecules. So far, he has mentored 7 PhD students. He and his group have published 77 research journals, from which one of his research scholar has received the S.S. Bhatnagar Young Scientist Award recently in this 2020 in the Indian Chemical Society month-long August Symposium, RACMS, and the Acharya P.C. Ray Memorial Young Scientist Award in 2018. And apart from his research publication, Dr. T.K. Mishra has also great contribution to the academic conference through his work such as the 100th Indian Science Congress 2013 Calcutta University, to name a few, and several other 27 conferences. So now I welcome Sir and I invite Sir to take his part. on this lecture. Welcome, sir.
Okay, thank you very much. If you have any problem for listening or uh, viewing the slides, so you just let me know. Maybe some network problem will be there, so it will be I will try to improve. Okay, now come to the function. So first of all, I am really grateful and honored to get this opportunity to give a talk as a annual memorial talk of Professor Jason Paul. So obviously already mentioned that he was a great professor, so and produced many great students. So really I am grateful for getting this opportunity. And I'm also grateful to Diyamai frequently contact me and asked me to give the talk. So thankful for this opportunity, arranging this opportunity. And obviously the HOD of the department, St. Anthony College, Dr. Sanitang, and the former already HOD couldn't join, that is the Manoj Gupta, the student of Professor S.N. Paul, and other faculties, other researchers, students. So far I have seen there almost 114 participants joined this program. So really, whatever the endeavor you have taken at the very beginning, it is successful, what I can say. Okay, so let me come to the today's talk. And for this talk, it is understanding the basic knowledge of nanomaterials. Okay, first of all, let me know the share screen. Okay. It is visible now, screen?
Yes, sir, it's visible.
Okay. Okay, so today's talk, that is the understanding of basic concept of nanomaterials. And already I mentioned it is a tribute lecture to the Professor S.N. Paul. That opportunity given to me. So the concept is the nanomaterials. So first of all, let me tell you, because I think almost the many students are there, undergraduate students are there. So they are also in the future what they will want to do and what actually happening in the advanced research level. So there are many areas. One of the areas, that is the nanomaterials. Nanomaterials, it is a broad name. Engineering side, science, physics, biology, everywhere. Now the research on the nanomaterials is going on. Everyone trying to getting the new result, and obviously new results are there. Just to let you know that one thing is that the semiconducting materials, that's also in the nano level, in the nanomaterials level. The people are trying to explore the new results. So it is a very broad area. In the biology, the scientists are trying to develop the nanomaterials for drug delivery. These are actually very specific to deliver the drug that is in specific region or area where the actually affected. So drug delivery, that is one of the important research field based on the nanomaterials. Another is the sensing. In the sensing field, sensing is very much important for environmental science, for diagnostic process. There are many areas. So sensing is also important. Semiconducting materials I have already mentioned. So there are huge area and huge scope. Anyone can explore. Anyone can choose the different areas in the science field. In general, it is the science field. So they can explore the many things. As it is the actually basic, so I giving you the broad aspects of this one. So that's these different areas you can do, you can think about. You are right now in the undergraduate level, those are already research field. They also in the field, they also do something, think about. Okay, one for the undergraduate student, I am just informing you, it is not like that we are sitting and thinking and we are think about, okay, I will do something. It is not like that. So now the different types of journals are available. So it is my advice, you read the journals in the different fields. And if you get interested, then you can read more journals, develop your brain, and then you can start the research. Study is the one of the important thing whenever you are going to do something. Without studying, you cannot do anything. Okay, so this is the very just simple advice to all of you. Now the next come to the point in the nanomaterials. So in the field of nanomaterials, so it is the nanoscience. So nanochemistry, there is a nanotechnology, all you can club to form the nanoscience. You can say the nanoscience. So before to say something about the nanoscience, first of all, we have to mention the name, the Richard Feynman. Richard Feynman. He was actually a physicist, theoretical physicist, and he was given a very useful lecture. Encourage that lecture actually encouraged all scientists, and this was given in the annual American Physical Society meeting at Caltech on December 29, 1959. What he told, the quotation, now we can say, there's the plenty of room. There's the plenty of room at the bottom. There is a plenty of room at the bottom. An invitation to enter a new field of physics. Okay, so he was just told that you must think at the bottom. At the bottom level, we can start something. We can develop something. He suggested that it should be possible to make machine. It should be possible to make machine at the nanoscale that arrange the atoms. Just think about, just it arrange the atoms the way we want and do chemical synthesis by mechanical manipulation. So you have to catch the atom. If you want to make a building, you need the brick. Bricks you have to place one by one to make a building. So here is also atom. That is at the bottom level. If you arrange in different way, so you can prepare some interesting results. So what is actually the nanoscience and the nanomaterials? Here I can mention you one thing, especially chemistry, physics, we know the atomic level, the molecular level, and also we know the bulk materials, So nanomaterials or nano matter, it is in between this. It is in the nano range. As we know, the atom, molecule, these are less than 1 nanometer. And the different type of crystals that we can observe, that we can see, that is greater than 100 nanometer, and the bulk material. So in between this, that is the nanomaterials we can see. So that is in the nanometer range. That is in the nanometer range. So what is the nano? How small it is? It is a Tata Nano? Yes, that is in the car level. What we can say, this is the nano, Tata Nano, small one. But that is visible, you can see. But in case of nanomaterials, now in the nano range, less than 100 nanometer.
Excuse me, sir.
Up to 1 nanometer. Okay.
Your slide is not in full screen, so if you can make it full screen, there is that.
Full screen. Okay.
Yes, yes.
It's okay?
Yes, sir. Thank you, sir.
Okay. So, so that is in between this. That is in between this. And this level actually can observe some physiochemical and optoelectronic properties. That is in the nano size level we can observe. Okay, so how you can imagine that how small it is. So if you arrange the 10 hydrogen atom, so that is, it is the 7 nanometer. DNA, that is 2.5 nanometer wide. Human hair, it ranges from 50,000 to 100,000 nanometer wide, just white. So that you can, in your naked eyes, you can see. So from these different types of things that is around you, from there, now you can get idea that 1 nanometer, that is 10 to the power minus 9 meter, how small it is. So now the question is that how we can observe, how we can measure that nanometer range. So there are the developed different instruments are there. Atomic force microscopy, scanning electron microscopy, transmission electron microscopy. So these are the different instruments from where you can, this is actually very high resolution microscope, from where you can see the materials you synthesized in the nanometer range, that is you can observe. From the time where you can get the perfectly the nanomaterials, if it is spherical, you can observe it. It can be different shape. If it is cube-like, if it is triangle type. Okay, so that is one. scanning electron microscope, it is also, you give the surface, because now what people are trying to do, they are not only synthesizing the nanomaterials, they're trying to functionalize it. So after functionalization, they use the different materials. Suppose I already mentioned the drug delivery. If you're trying to attach the drug upon the nanomaterials, so you have to observe whether it has been attached or not. So in that case, the scanning electron microscope is very useful. Atomic force microscope, that topology nature, also you can get. And from their size in the, if it is spherical, very easy, you can get the diameter. If it is cube-like, so in the different sides you can get. So that is the different sophisticated, very costly instrument used for studying the nanomaterials. Other different instrument, that is the powder X-ray diffraction. Powder X-ray diffraction. So this is actually another instrument. From there, by using this one, you can get the crystallinity. Crystallinity, as you know, in generally what we do, we can try to develop some single crystal. There is single crystal analysis instruments are there also. From there, you can get the molecular structure. But it is, if it is powder type, if it is powder type, not amorphous, powder type, and that has also the crystalline in nature. So in that case, XRD instrument can be used. XRD instrument gives, it is actually the plot of intensity versus 2 theta, that is Bragg's equation using. So that can be get the crystallinity, that different planes, as you know, if you have the crystal idea, so there are the different lattice points. That means the different lattice point, just simple face center cube, body center cube. So from there, the different planes having the maximum lattice point. So from there, they reflect the incident light. So diffraction light, their intensity. So you can get idea from which plane it is. So from the nature of the plane, you can predict the crystallinity of the materials. So that is another way. Dynamic light scattering instrument. This is also one important instrument. In solution, that the particle size gathered and their distribution, we can get idea. It is generally, sometimes we call the hydrodynamic size, hydrated one, and the size of 10 and DLS, that is different. Okay, zeta potential, the nanomaterials, what type of charge it is carrying, millivolt, we can measure whether it is positive or negative. Another important instrument is ultraviolet visible spectroscopy, UV spectroscopy. From there also we can get the UV spectrum different idea. That I will discuss very details. Okay, there you can find. So this is one of the things, is that when you are synthesizing some materials, so you have to characterize. For the characterized point of view, so these are the very important and useful instrument that you have to use for the characterization of the nanomaterials. So what the different types of nanomaterials? That is simply, it can be the nanocluster type, it can be the nanopowders, nanocrystals, it can be the fine particles, quartz particles. So based on their particle size, different size. So these can be classified. Another one thing we generally sometimes we misinterpret that colloids and nanoparticles. Colloids and nanoparticles. So colloid particles, that is in the nanometer to micrometer range. But the nanoparticles generally consider it is the range 1 to 100 nanometer. 1 to 100 nanometer. Okay. So these are different types of different nature of the nanomaterials that you can get when you are going to developing some nanomaterials. It is not the new one. In this slide, I just let you know. After the lecture of the Feynman, Richard Feynman, it gets some impetus. People are trying to explore something. So use their enthusiasm in the field. But it was from the very earlier, it was also existed. In the here the different types of cups are there. Roman, that is the colloidal gold. And this Lycurgus cup, it is actually a bronze cup. And in the glass, according to the museum, this glass contains 70 nanometer particles that are an alloy of silver and the gold. So that means it indicates that peoples are used before, much earlier, but maybe without knowing the thing. Okay, they developed something, they got different color, they make this one, but without knowing what is it, it was like that. But after the Feynman, it was get impetus. Now, there are that here in this slide, actually, I would like to maintain. This is the one thing I already mentioned. The nanoparticles, it is actually the bridge. It is the bridge between the molecular and an atomic state and the bulk materials. Okay, so from the atomic or molecular state, you can start for synthesizing nanomaterials. To get it, you can start from the bulk materials. So that's why this is in the two process mentioned. One is the top-down method. Another one is the bottom-up approach. Top-down method and the bottom-up approach. So in the top-down, that is from the mining process, you have to break. You have to take some materials, maybe in the centimeter level. Then after breaking to get the fine particles in the nanometer range. So that is what we call the top-down method. Another method that is the bottom-up approach. So from the atomic level or molecular level, you have to reach the nanoparticles range. Different methods are there, liquid phase and the gas phase methods. But the basic thing what I would like to say, that is the atoms and molecules. Atoms and molecules, these are very atomic level and these are very energetic one. So to control them, it is very difficult. If you reduce some ions, it will form the atom. Then once the atoms are formed, they will aggregate. They will aggregate to form the nanomaterials. Not the nanomaterials, they will form the bulk materials. Okay, in a solution, you know, the silver ion is there. If you give the hydrogen for the reducing agent, so you can get the silver precipitation. So that is, you can observe. So that is the bulk nature. So to get the nano, you have to stop. You have to stop in some level, their aggregation level. Okay, so their touch. Okay, so here that I will discuss again, that how you can stop the aggregation one, because we have to, generally we are the chemist and other things, they follow the bottom-up approach. So for the bottom-up approach, they have to stop the aggregation. So to stop the aggregation, they have to do something. Okay, so here you can see this is actually large surface area to volume, because nanomaterials, they are actually different from the bulk materials for these different properties. Okay, in the slide here you can find the large surface area to volume ratio, large surface energies, Plasmon excitation. I will discuss the Plasmon excitation, what is it, quantum confinement, short range ordering, a large number of low coordination sites. Okay, so there are the different properties of the nanomaterials. They have the different optical properties, sensing properties, catalytic properties, different than the bulk materials. So that's why actually everyone trying to explore the nanomaterials. What I think today, whatever the different types of reactions, different types of properties already explored, that can be re-explored using the nanomaterials. So using the nanomaterials, you can get the different result. Okay, so there are huge scope for this one. Okay, so this is one, this slide one, I let you know that from the bottom-up approach, when you are reducing some ions to get the nanomaterials, you have to stop the aggregation. What I say, ions to atom, then atom aggregate. And due to the aggregation, they will form the bulk. You have to stop in the nanometer range. So that's why generally in the field of the bottom-up approach, some of the capping agent, or what we call stabilizing agent, are used. Capping agent or stabilizing agents are used. So this is the different types of molecules you can use. Different types of molecules you have used, that may carrying the positive charge, that may carrying the negative charge. So that will adsorb onto the surface of the nanomaterials. And when it adsorbs, so that particles get charged, maybe positive or negative. So after having the charge, they will create one electrostatic barrier. They will get repulsion from one particle to other particle. So by this way, they can be stabilized in the solution. So this is one of the most important technique from the bottom-up approach scientists are used for synthesizing the nanomaterials. So there are the various, so far, various capping agents have been tried for stabilizing the nanomaterials. Here you can see there are some, this one. So these are, sometimes these are also neutral, and some are carrying the positive charge, and some are the negative charge. I will show you later. Here is also some of the stabilizing agent, that citrate, gluconate. So these are different stabilizing agent are used. Okay, now one thing is that when you are using the different types of capping agents, whether it is positive or negative, whatever, so it will adsorb. What type? It may be chemisorption, it may be physisorption. Chemisorption means it can form the direct bond with the nanomaterials. This is the simple nanomaterials. Think about a small ball and some other molecules that make a bond. That is if the sulfur link is there, so sulfur is very much affinity toward the silver and gold. So they form the direct bond with that one. And once they make the bonding with the nanomaterials for stabilizing the nanomaterials, so what happens? That one then used, then can be treated as a simple organic one. And that cannot be dispersed in the water. So that cannot be say these are biocompatible. So for the biocompatible, you have to get the water dispersed nanomaterials. So to get the water dispersed nanomaterials, you have to choose some capping agent or stabilizing agent that can physically adsorb. That sometimes you can remove that one also very easily. Okay, some dialysis process are there. You can remove this. So, but is it not possible for using the stabilizing agent that chemically adsorb onto the particles? Yes, it is possible. In that case, you have to use the bifunctional capping agent. Here you can see that this one, thiofluorine. So there is a carboxylic group is there, their sulfur is there. So it can form the direct bond. However, it can easily make the solubility in the, not soluble, what we can say, it is dispersed in the water. So this is the different nature of the capping agent from top down bottom up approach. You can use whatever materials you are going to synthesize, that you can think about. So first of all, we have to mention generally the very beginning, the nanomaterials, nanoparticles, that is in the silver and gold, it was used using the citrate. Citrate initially it was, and nowadays also the citrate stabilized particles first of all synthesized, and that can be functionalized by the different you desire study, you can functionalize. So these are actually the very beginning this method was developed. It is I think 1979, then it was modified in 1982. So there are the two methods, citrate. Now another one thing actually, so you have to think about in the bottom-up approach. So one materials require that can reduce, can be used as a reducing agent, and another one that can stabilize. However, you can use one thing that can do the both role, dual role, stabilizing as well as reducing. So citrate is such an agent that can be used as a reducing, as a stabilizing agent. However, what happened? In that case, the particle size is somewhat bigger. However, in case of you can using the citrate as well as if you use the sodium borohydride, so the particle size is very less. It is 9 to 20 nanometer. Okay, but here it is more than 30 nanometer. So this is the very beginning method is you can get. So these are some particle size from the TEM image where you can get the particles. So here you can find that from the TEM image, this is the transmission electron microscope. So from here you can get the particle size. From there you can find the distribution, and there also you can find the different planes. Okay, this is that deflected planes, selected areas pattern. So from there also you can get the different idea. Just I give you the one thing that how the C looks like the nanoparticles. Okay, so another method means this is also the bottom-up approach. However, generally the people say it is the green method. Another way people are synthesizing, because in our nature there are different types of medicinal plants are there. There are different types of fruits are there. Generally we use, because if you use some chemicals for stabilizing agent, so that may be the toxic one. However, if you get the materials from the nature, from the fruits, from the leaves, so that is that component we can use for the synthesizing the nanomaterials, so that it is the in your body that it will be the very, very less toxic. So as the citrate is used, so the citrus fruits are generally used for synthesizing the nanomaterials. Okay, so I think it is clear that green method means you can use the different types of fruit juice, apple juice, pear. Okay, you know the different types of different areas. The folk medicine also, different fruits and leaves, they use the folk medicine. So you can collect those things. You can explore that thing. In our research group, we have chosen one citrus fruit, that is Citrus microptera. So this is the very rare fruit in the Northeast. It is available. So my research group used this one fruit juice to synthesizing the gold and silver nanoparticles. And after that, we use some anti-biofilm study we have done. Okay, so later I will show you. So this is that fruits. Okay, Citrus microptera. So using that one, we have synthesized the gold particles. So you can observe this one, and this is the TEM image, and this is the XRD. Okay, from there we can get the crystalline nature. Okay. Another important thing is that nowadays I mentioned the TAME, SAME, FM, but the research is now in such a level, in such a bottom level, that now using this is, I think, scanning tunneling method, STM microscope, STM microscope. So from there, you can get how many particles, how many atoms are there, how many atoms are there, and how the different materials attached with this one. So this is actually, I thought, is a very interesting one. It is one paper published in Nature Communication in 2018. There, the metal core of the particles that is explored, that there it is found that 374 silver atoms are there, and that surface is protected by a set of tertiary butyl benzene thiol. You see, both are all are observed. So such a very interesting figure they can get from studying this one. So if you wish, you can study this journal. Okay. Now you get the materials. Okay. Now just I say you get the materials. However, there are the different methods are there. From the different methods, bottom-up approach, I just mentioned the chemical reduction method. Chemical reduction method using the nature materials, that is also some reduction method, and some other various methods are there. So once you get the materials, then you can think about that what would be its applications. Okay, so here we find the different shape, because the properties of the nanomaterials that extremely depends on size. If their size is different, the properties will be different. Their activity will be different. Shape, size, shape, refractive index, all there are many environment of the nanomaterials, surrounding environment of the nanomaterials, all are very effective to tune the properties of the nanomaterials. So these are the different, just figure here you can find the different nanocubes, nanorods, nanosphere, nanoflower, nanoprisms. Very interesting, the different words you can find. Okay, so that can be prepared in different way. Irradiation method, this is also another method. Just UV light, you place the UV light by you can reduce and get the materials. Physical, chemical, and biological, there are different methods get the different particles. Here, okay, before describing this one, I come to this slide. One interesting property of nanomaterials is its surface plasmon resonance. As I mentioned earlier, that in the different instrumental method, UV-vis spectroscopy method is also very important method. So from there, you can get the surface plasmon resonance absorption peak. So that peak vary due to the change of the size and other things that I will show you. However, before that, we try to get what is surface plasmon resonance. What is surface plasmon resonance? This is very interesting property of the nanomaterials. And due to these surface plasmon resonance, silver, gold, copper, iron also, they, especially silver, gold, they in the UV visible range, you can get their absorption peak. You can get their absorption peak. So what is it is surface plasmon? It is not like that the simple in the UV spectrum. What is the principle of the UV spectrum? What we know that it will absorb that the your compound or whatever in the solution is there, it will absorb the light, and after the absorption light, it promote to the higher energy state. So to promote this one, the energy gap, that equivalent radiation it absorb. So that is the absorption method. That is the absorption method for electronic transition. UV, it is the electronic transition. But in case of nanomaterials, that is not the electronic transition, but we are getting the UV-vis spectrum. So that is due to the surface plasmon resonance. Surface plasmon resonance, to get it, here you can, in this picture, there is find the two sphere is there. So it is just a nanoparticle, but you can think about just it is an atom. It is an atom. If it is an atom, so it will have the nuclear part, it will have the electronic part. So if it is vibrate, so it will fluctuate. So sometimes the positive and negative, they will be in the different end. Electron cloud and nuclear part. So it is, just think about, it is always the vibrate. And due to these oscillation, what we can say oscillation, it will form a wave, electromagnetic wave. Electromagnetic wave. So these electromagnetic wave, and when the some light is coming, so if both these resonance matches, that it can absorb that light. Absorb that light. So that is the surface plasmon resonance, and that absorb the light, and that you can get in the UV visible spectrum. So in this case, we have to mention Gustav May. He was actually developed the microscopic Maxwell equation, and to calculate the extinction, scattering, absorption, cross-section of the gold nanoparticles. And he showed how the spectra changes as a function of the particles. So the optical resonance in a noble metal nanoparticle, silver, gold, that is at the collective oscillation of the conduction electrons, what we call this is conduction electrons. That term we call the surface plasmon resonance. Okay, so they form actually air stable colloids, and due to the DD band transition, plasma frequency. So whatever, so from there you just get idea what is surface plasmon resonance, and for these you will get the UV visible spectrum. Now in this spectrum you see that how the different, due to the different size in the different region, they absorb the different light in different, also different color. Okay, so UV-vis spectrum, that is a very interesting one. From there you can get idea of the, different size and their color, different properties. Okay, so this is one. This is another one thing I would like to mention here, that in the UV spectrum we'll get the different region, the light absorption is there. So this is due to the vibration of the electromagnetic wave. Okay, it may be the transverse, it may be the longitudinal. If it is the transverse, it appears in the lower wavelength. and if it is the longitudinal, it appears in the higher wavelength. So this is the different mode of vibration. You will get the different. So this is actually for the shape, different shape. For the different shape, you can get this different type of vibrations, wave, and absorption in different areas. So the factors, that is, I will discuss little bit here the surface plasmon resonance. So how it is affected? It is affected by the size, morphology, the composition, that is the surrounding environment, and their surface chemistry. So that tune the properties. Here in this slide, here you can find that how the surface plasmon resonance changes due to the different size of the particles. The size generally decreases from 20 nanometer. It is near about the decreases from 20 nanometer. But in the earlier, that is the black one you can find, and after decreasing it will blue shapes, but then it is turned over to near the 12 nanometer, and then it start the red shape. So from there you can get that the size that affects the surface plasmon resonance. Here is also the someone synthesized the nanoparticles, that is using the oleyl amine, and now you're trying to replace with the hexane decanthiol. So you're changing the environment. You're changing the environment with some other chemical reagent. So due to the change of these, the nature of the surface plasmon resonance changes, because there is some changes of the refractive index, the changes of the size, because different capping agent that has the capability to stability in different regions. So that is one thing. So by using this surface plasmon resonance, there is the huge application in different sites. It can be used as a chemosensor, it can be used as a biosensor, drug delivery, medical diagnosis, biotechnology, environmental protection. There are vast areas. Just simple, utilizing this surface plasmon resonance, you can explore, you can study these different properties. So metal nanoparticles, if we just confine our attention the metal nanoparticles, so we can find the metal nanoparticles that can interact with the biomolecules, that can be used as a bioanions. That actually in my research group it has been done. Metal nanoparticles for sensing the environmental polluted cations, catalytic activity, and the biophil inhibitors. Okay, so I can continue, no? Is there any time limit? DMI?
Yes, sir, you can continue.
Okay, so I can just little bit continue.
Yes, sir. Yes, sir, you can go on.
So you are not boring, I think.
No.
Okay.
There are so many questions coming out.
Okay.
Okay, sir.
So this is actually the slide what we explored, that metal nanoparticles, how it can interact with the biomolecules. So in the case of biomolecules, when you add the biomolecules, so suppose in the stabilized metal nanoparticles synthesized, and now you introduced in your body, so the biomolecules are there that can interact. So that may how they can interact. They can interact just different electrostatic force. It can use some hydrogen bonding interactions. So it may reduce. It may bring the particles in close. So when it brings the particles close, so their surface plasmon resonance will change, and that can be used to monitor that how it can interact. So here the silver nanoparticles, where we can find that some surface plasmon absorbance, it is 392 particles, 392 nanometer. Size is near about 10 nanometer. Okay, these are the FM image. And these are actually some macromolecules. This is some molecules. These are generally considered as a mimic of the biological polyamides. So if we study that how the particles interact with these biomolecules, so we can get idea when you can use for a biological purpose for the nanoparticles. So you can get idea that how it can interact. So from there we can get the different one. Most important is when the silver nanoparticles, how it behaves in presence of macrocyclic polyamines. Is there any aggregation or kinetic effect? And if there kinetic effect, whether we can study it? Okay, now it is little bit higher level. You have to get idea that how you can study this one. Okay, so let me see here. Here actually the simple what we have seen, that if you change the particle size, the surface plasmon resonance changes, and in there also polyamine you change some thiol, so there is also some changes. However, my question is that whether this interaction, it is all of a sudden it changes, or it changes the kinetically, that very slowly it can replace. Okay, so most of the cases the people are not studying this kinetic effect, but my research group studied this kinetic effect, that how kinetically we can control, we can measure the effect, the rate, the way they interact. So with the time absorbance, if we plot this one, we can get the different types of kinetic, how it changes. So from these changes, we can get the absorbance rate constant K observed. And Moskovitz and Blikova, there is a journal, 2015 physical chemistry journal, you can find there they related that how this rate constant related to the concentration of the substance you are adding. So we used this technique and study the kinetic effect. There is actually the same image, that from there with the addition of the things, how the aggregation takes place. From the same image also I will show you that how the aggregation from the same image also you can get how it can aggregate. So this is one mechanistic way. Yeah. Now here you can find from the rate constant that K observed, if we plot with the concentration, so from their graph actually after certain times we can find that how much of the foreign substance you are adding that can tolerate the particles, get the stability. But after that, there is immediate change. and there is that rate constant remain constant. So from there you can get the minimum coagulation constant. It is actually the concentration of coagulation concentration. So that is the minimum concentration, optimum concentration that you can get. Okay. So from there, here is also another, from these, if you study the kinetic one, you can get absorbance, the rate association, that molecules you are adding. So in the surface, the particles, one chemicals are there, so they will associate. They will associate. So these association constant also you can measure. So that is one technique we developed. This one. So this is different data. Here is also another, this reagent we used for synthesizing the particles. And one thing is that it makes the particle positive. It makes the particle cationic in nature. So once it gets the cationic nature, you can use it for sensing the anion. So here actually that is the reagent we call Bratton-Marshall reagent. So this is fluorescence active. So using the fluorescence, you can also characterize and control the different methods. So in this where we will see that not only the UV1, but the fluorescence method can also be used for study the sensing one. Here is also we have seen that at different pH, their color exhibit the different color. So these particles can be used as a pH sensing. Not only that, it can be used as a pH sensing. Okay, pH sensing. And here we explored that one citrate ions, different types of succinate, malonate, oxalate, different types of them, the citrate ions. That is very useful one for the diagnostic purposes. So that can be sensed using just simple UV-vis spectrophotometry. UV-vis spectrophotometry. Okay, so here is also the same thing. I am not going to discuss too much. Okay, so another one, we have used the gluconate one as for synthesizing the particles, and that can be used as for sensing the lead, because it makes the particles anionic. So it can mix the particles, so you can use for the cationic sensing. Okay, and one thing is that this method is so useful, so accurate one, that after sensing the lead, we know the EDTA, that is a very good complexing agent. If you treat the EDTA, then it will reverse back. So that gives the accuracy of the method. So there are different calculation methods. We can get their minimum concentration range and maximum concentration range, how we can determine. Okay. So it can be used also catalyst. It can be used, particles can be used as for the catalyst. One method generally people are used, that is the 4-nitrophenol. Sodium borohydride cannot reduce it. But if you use the particles catalyst, so that can reduce. Here the method, how very simple method people are used, we have also done. So the nitrophenol, actually this is the phenoxide. Now once adding the particles, so they form this one. So this is the one of the application site what we explored, that is showing here. Here is in the mechanistic path, that how particles can be used as a catalyst. Actually, I will show you one interesting one. This is one interesting part I am going to discuss. This is as you know, nowadays, the bacterial adaptation. We know that we are studying the antibacterial effect. Antibiotics are there. We are using the antibiotic drugs, but bacteria now cope up with this antibacterial term. They develop the different method to fight against antibiotics. So that's why now scientists are trying to think about the alternative method. What method they developed? They developed some bacteria. Now they developed the biofilm. Biofilm, this is one of the mechanistic part they develop when they attach with some area, some substance, they develop the biofilm. And the biofilm, antibiotics cannot prevent, cannot destroy, cannot enter, cannot penetrate the biofilm. So you have to think about the alternative. So that is the biofilm, anti-biofilm effect you have to study. So what we have studied biofilm, that is thing. So this is the different attachment and how with the attachment, how it form the biofilm. Okay, so bacteria develop the biofilm, the fight against antibiotics, what we take to kill the bacteria. Okay, but so we have to now develop some drug that can inhibit, that can penetrate the biofilm. Okay, so these are we have seen here. This is the slide you can see from the same image. So this is the biofilm. This is just think about it. It is a blanket. It is the one blanket. So and under this blanket bacteria is the very active. So if you treat here azithromycin, that is the B1, we have treated the azithromycin. You see some little effect is there. But it cannot expose the bacteria. But we have used that iron nanoparticles, green synthesis method, and that you see with the increase of concentration, now it destroyed the biofilm. Now it exposed the bacteria. And at higher concentration here, it is clear, it is not the very clear picture, but it ruptured the bacterial cell. Okay, so that is the way, one of the important method you have to develop to fight against the bacteria. Okay, so this is, in this case, the metal nanoparticles, the nanomaterials you can think about. Okay, and another method actually people also try to do with the antibiotics. If they functionalize the metal nanoparticles with the antibiotics, so that is also in some cases the better effect, the better result giving. So I think so these results I think encourage me that not only that nanomaterials synthesizing, but how it can be utilized in different methods. Very few, and whatever my area actually I am doing that I just showing you, but this is the very small part of its application. Antibiofilm, that is very interesting part. You can do it. Sensing, I have seen that within different biomolecules are like that. But it has the vast area for the nanomaterials, different areas, different field. The people, the student, you can choose and you can explore the application of the nanomaterials. Okay, so thank you very much. Thank you very much once again, DMI and the St. Anthony College, HOD and others for giving this opportunity for it is actually the online, the situation developed in such a way that now we are interacting the online, but it is really I'm missing my the dais, the audience. All are there, but I am missing. Okay, this is I think one limitation of this online method. Okay, so thank you once again. Thank you very much.
Thank you, sir. Yes, we missed the applause that we are supposed to give to you. However, thank you very much, sir. And I hope the audience has been benefited a lot. Thank you, sir, for enlightening us with the basic properties of the nanomaterials, their synthesis and application. Now we will open up for question round, and I have seen that there are a lot of questions even before this resource person could completed their questions have come out plenty. So we will try to answer a few questions due to time
Yeah,
restriction. No, so
already I have taken the much time.
no, there are so many questions. Like I hope the audience have been listening very well. That is why a lot of questions coming out. So it's there in the question and answer. And so I've jotted down some of the question. So what is the size range for nanomaterials that can be used for XRD?
For the nanomaterials, the size range.
Yes, what is the size range for
I
nanomaterial
think
that can be used for XRD?
actually it is in the powder form. Generally, in the XRD, we use in the powder form, or it is in the we can make the thin film for studying the XRD. Okay, so you have to be the crystalline range. Generally, what we call that is more than 100 nanometer. Okay, so if it has the crystalline nature, so you can get the XRD peak. Definitely, I cannot mention that what the range is there, but I can say you that crystalline nature must be there, because from the XRD we can also determine the size. Okay, some mathematical formula is there. From the actual width of the peaks, we can get the particle size. But one thing is that if you want to get the very good peak, it must be the crystalline nature. I think amorphous and crystallinity, all you know. So crystalline, you can get a very good peak from the XRD. Okay. Next.
Okay, some more question. Which nanomaterials are used for cutting tools? Which
Nanomaterials is cutting tools.
yes.
Okay, that is actually beyond my idea.
Yeah.
But I just say you know, due to these nanomaterials, everything is going to small and small. Okay, but in case of mobiles and other thing, we can get the bigger one to get the bigger picture. Okay, but the resolutions and other things for development we can use in the nano range. Okay, but what actually the nanomaterials used for the cutting tool, that's I don't have any idea.
Okay, so I think this another question is within the topic that you have discussed. What are the optical properties of nanomaterials? So someone want to know what are the optical properties of nanomaterials?
Optical properties, that is the already mainly I discussed. So that is the one of the important optical properties, that surface plasmon resonance. So due to this, I think I was able to clear that what is it surface plasmon resonance and how it absorbs the light. So this is the most important optical properties of the nanomaterials. However, optical properties using it can be used in semiconducting materials properties. They also can be used the solar cells. So using if you tune some materials in such a way, they can absorb the light and show some interesting properties. Chemosensing, biosensing, drug delivery, all these we can, the most important that is surface plasmon resonance, we can use such property and to explore the optical properties. There are many other properties are there.
Okay, so regarding with this property, I think this same question is related to surface plasmon. Like, why is gold used in surface plasmon resonance? So some of the audience have asked this question. Why is gold used in surface plasmon resonance?
Why?
Why gold is used in surface plasmon
Oh,
resonance?
what goal? What goal? That
Yeah.
is
Why
whatever.
gold?
My goal. My goal. That is already. Today we have discussed that surface plasmon resonance. Due to this surface plasmon resonance property, particles absorb the light, especially silver gold, in the visible region, and these extremely depends on the size, on the environment, on the refractive index. So what I have shown for the chemical sensing, for the sensing purpose, you can use. That is, suppose you in a solution, you have some materials, you have some contamination you are going to sense. So if you add that one with the particles and measure the surface plasmon resonance, so from their change, you can monitor, you can quantify. So that is one important method is the chemical sensing, biosensing, drug delivery, diagnostic method. There are huge application of surface plasmon resonance. Surface plasmon resonance, that is the UV spectrum. Okay. And obviously also fluorescence spectrum you can use. Okay, based on the functionalization. You can functionalize the materials to the fluorescence active. Okay.
Okay, so there are a lot of questions, but I think if we ask, it will not. The lecture will not end.
Okay,
So
I can. You can do one thing.
we
Okay,
can
you can share my email.
send. Yes,
Okay.
I think we can share your email and the question also. I can share it to you so that the audience will get the answer, because there are many questions which are beyond the lecture, which are beyond the lecture also. So only one last question, and I will allow to my colleague if they have any questions. So, how are nanoparticles prepared from plant extract? How are nanoparticles prepared from plant extract?
Plant extract. How
Yes.
can we prepare from the plant extract?
Yes.
Simply extract method. It can be water. It can be the different solvents. So extraction means in the plant means if you the leaves are there in the water, you just boil it and get some extract. If you have the fruits, you get the juice. Now simply in your extract, in your juice, you add the your desired uh, compounds. Suppose if it is the silver, you add the silver. If it is the iron, you can add the FeCl3, copper, CuCl2, whatever you can add, and you can just heat it. Sometimes it is that is the condition you have to set up. Sometimes maybe simple stirring, you can get the color change, you can get the particles. Sometimes you have to warm it. Okay, so very simple. Just you get the extract It may be the water extract, it may be the pure juice, it may be the pure juice. Okay, so use for the reducing as well as stabilizing for the particles. Very simple method.
Okay, so I think there are one more very important question is coming up. Can a molecular structure be generated using XRD?
Molecular structure
Be generated using XRD.
XRD. No, it is actually, if it was possible, then single crystal का कोई जरूरत नहीं था.
Yeah. Okay.
That is single crystal analysis. But from the XRD, we can get the crystalline nature. Whether FCC, it is BCC, whatever. So that idea we can get from the, because it is the light deflected from the planes where the different lattice points are there. So it reflects the lattice points, planes of the crystals. Okay, not in the electron density map, where in the single crystal we get the electron density map. From the electron density map, we can get idea whether it is what type of atom it is. So based on that, you can make the molecular structure. So from the XRD, it is not possible. You have to use the single X-ray crystallography.
I will allow our colleague, I think our head, she has some question to ask. Okay, if she doesn't have any more question, I think one question again is there, although there are many questions, but one question is there, like someone want to know, they want to pursue the study in nanomaterial and how can one move toward the study? What options are available?
What? Kindly repeat it.
Okay. What options are available for aspirants who want to pursue the study in nanomaterials and how can one move towards this study? So someone want to study nanomaterials, so how can he or she pursue the study? They want to know about that.
I don't know actually in what level he or she is studying. Okay, but you can choose first of all if in a master level or MTech level, whatever the level is there. So from there, the defense actually different. Generally, we are the basic science. We generally in the basic level research we do that for the application side. Generally, the engineering field, they use the particles in for the different purpose and develop the different device. Okay, so electronic communication, that is one of the field one can choose. Bioengineering field can choose, they can use the materials for the biofield. Okay, and physics, that is one of the important area. Different semiconducting areas are there, so they can for the physics field they can explore the different properties from there. So in every branch of science, there is a scope. Not only the scope, what I can say that everyone right now, everyone focusing their research in the nanomaterials. For engineering, they are trying to devise some devices, and we are trying to explore some properties and obviously some applications. And here is also, I just said that how in the drug development, you can explore the use of the drug development of the different nanomaterial. So in every field, there is a scope is there. And the very beginning, I mentioned you to choose the certain area. You just think about the certain area and just start studying. different types of journals, what type of the advanced research is going on. Based on that, you fix your goal. Okay.
Okay, thank you, sir, for giving
Thank you.
advice, and I hope the audience are benefited from it. So, any further question, we will send the email address of the resource person to in the WhatsApp group. So, if any more questions is there, so we will send to the email. So now I will call our head, Dr. Isida Lin, to give a word of thanks.
Okay, thank you.
So first of all, I would like to express my gratitude to our principal, Reverend Brother Dr. Albert Longley Dekhar, for giving us this opportunity to use the Zoom address of the college to hold this annual SNPAL Memorial Lecture. Because without his permission, again, we cannot use this one. So then I would also like to thank all the participants who actively participate in this lecture. We can see your enthusiasm, we can see from the question and answer which you have posted here. So we will make sure that we will try, so will try his best to answer each and every question. I would also like to thank my colleagues. All of them have wholeheartedly worked together to make this event a successful one. Especially it's the first thing for us. It's our first time to host an event like this online. So I would like to thank all of them, especially to one of our colleagues, Professor Fernando Dindo, who was the one who handled all the technical line, right from designing the brochure, designing the e-certificate. Then he is the one who conduct all these things here. So he is the one who, we can say single-handedly, he did all these technical lines. I would like to thank him also. Thank my colleague, Dr. Sudhir Langdamai, who compared this program. I want to thank Ms. Marily Saukami, all my colleagues who participate in this program. And last but not the least, I would like to thank our resource person, Dr. Tarun Kumar Misra. So we know that you are a very busy person, but still you spare your time to share with us here, to share your knowledge with us, with our students. And we want to thank you especially. We know that you are from, we can say NIT, but you have tried your best to come down to our level and especially to the level of the students. So we really appreciate you, sir. So we would like to thank you for all this. And I want to thank each and every one of you here, all the participants, especially with you. I hope next time, if we organize again another event, and participate again. So with this, I will conclude. Thank you, all of you.
Thank you.
Thank you, Dr. Isida Lin Saitang, for thanking us all, and thank you all the participants, and especially to Sir for this wonderful talk that we have this evening.
Okay,
So all the best, sir, for your future work also.
Obviously, sometime I come to you and meet.